Alright, so we've been working on sequences and series, other little random financial math. We're also going to talk about proofs, because proofs with series absolutely exist, but they definitely take a different form, because you can't just do only algebra, because every single term you add on is going to be different. So you'll notice here we're only assigning a couple. This is a trick. Proofs are tricky, so we're going to spend a couple days on it. Assign a couple today. We'll look at a couple more examples starting next week as well. So this method of proof is called mathematical induction, and we're going to focus on series. And induction works by proving a base case. So what that means is that you want to show that it's true for n equals 1, because remember, this is all based on series. So you start with the first term. So once you've shown it true for the first term, you kind of make a little argument. You say, okay, well, we know it's true for a natural number, and we call this k. So this is just a general natural number, and this is true since k could equal 1. We're using the scientific or mathematical version of assume, where we actually know it's true. We're just talking in general terms. And then what we want to do is, since we know it's true for k, we're going to prove it's true for k plus 1 here as our third step, because then we're proving it true for consecutive numbers. The idea if it's true for 1, and then it's true for 1 plus 1, then it's true for 2. Being true for 2 makes it true for 2 plus 1, which is true for 3. And then that proves it's true for 4 and true for 5 and so on. This seems like a weird kind of proof, but it works really well with series because we just keep adding on these integer terms each time. And the nice thing is that these first two steps are very straightforward, and you're going to basically be copying and pasting them each time. You're just going to be plugging in the new formula for whichever one it is. So in this case, we're going to start with the base case, and we're just going to say, okay, well, remember we're plugging in the first term, n equals 1, and you're just going to take the formula that it gives you. So this is saying that 1 plus 3 plus 5, here the sum of the odd numbers is equal to n squared. It's equal to a perfect square. So you're going to start with, okay, well, if n equals 1, that's 2 times 1 minus 1. And we don't write another term because you only want that first one, is equal to 1 squared. That's 2 minus 1, that's 1. Yep, this is true. So as I said, the base case, pretty easy. The next one, you're just going to write an assumption statement. I'll write mine, you can use your own words. You just want to cover these basic points. So here we're saying, okay, we know it's true for some k. And now we want to show that this being true for k shows that it's true for k plus 1. And so you'll notice in series, the difference between k and k plus 1 is on the series side, we still have 1 plus 3 plus 5 plus 2k minus 1, and then 2k plus 1 minus 1. So we added on this new term for k plus 1. And then on the other side, we've plugged in k plus 1. So we've just changed like the upper bound of the series as we went along. And it's really helpful to write this out because this is sort of like what you want. Once you have this, this is how you know your proof is done. Once you end up with this algebraically, you're able to put the conclusion on the end there, just like we would for some of our other proofs. So here's where the medium doesn't work all that well, and I'm going to have to do some erasing. Obviously, don't erase in your notes. I'm just making myself space in the video. So now we're getting to the algebraic part of the proof. And what you're going to want to do is start with what I'm going to call the k statement. So that's just this whole thing with k plugged in, right? And this is the thing from the assumption that we know is true. Like, we know this is true for some k, right? This is our k statement. Now, since we're looking for k plus 1, we're going to use the golden rule to say, well, I can add the k plus 1 term to both sides. So now we have our nice series with our new upper bound on the left-hand side here. So then we have 1 plus 3 plus ... out to 2k plus 1 minus 1 on this side. And that's our series that we want. And then on this side, we just have k squared plus that term because we're just adding the same thing to both sides like we normally would for like a solve problem, right? So add it on the left side, add the same thing on the right side. This is the golden rule of algebra. So the nice thing that's happening here is now we have the series we want on the left side. We have the upper bound now is k plus 1, 1 to k plus 1. That's great. That's the series side all sorted out for k plus 1. And then we want our new upper bound. We want to show that this is equal to k plus 1 squared. And this side is just going to be algebraic proofs. We're just going to do some manipulation to this whole thing and show that it's equal to this side. So the setup is kind of weird and different, but these are mostly algebra proofs. So if you liked the trig proofs more than your geometry proofs, this will feel much more similar to that than a 2-column proof. So I'm going to do algebra on this side to show that it's equal to k plus 1 squared, right? Because it's coming from the squared term here. That's how we know what we want. That's how we know that this is going to be done, is it looks like this side, because this side already looks like this side. So here I'm going to distribute like this, and I end up with k squared plus 2k plus 2 minus 1. Oh, plus 2 minus 1, I'm going to simplify to plus 1. And this is a lovely quadratic that we can factor, and it's k plus 1 times k plus 1, which is k plus 1 squared. Oh, look, we're done. We've finished our proof. We've got our conclusion, which you can write as QED, or just finish it up like that. There's more formal ways to write this. If you have a college professor or you have me in math theory, if you end up getting all the way through there, there are more rigorous induction proofs. But this is the basic format, and this is what I'm going to expect you to be able to do through distance learning. So, and we know we're done again because we now have k plus 1 squared matching if we had plugged in k plus 1 into this equation. Again, the base case and the assumption statement are going to stay the same basically throughout. So let's look at another example just to help you practice. So here we have a same idea. We have a series on this side. So all these powers of 2 add up to 2 to the n minus 1. So we've got our series on one side, our not series over here. Start with the base case. Say, okay, well, what happens if I plug in n equals 1? So that's just the first term. So here 2, 1 minus 1. Only one term because it's n equals 1 in the series. 2 equals 2 to the 1 minus 1. Here we've got 2 to the 0 equals 2 minus 1. Oh, these both equal 1. Excellent. We've used arithmetic to prove the base case. Then you can write your assumption statement. But the main thing that you want to make sure you're including with your assumption statement is that beginning of the proof, which is the equation with k. So we can start with our proof with 1 plus 2 plus 4 all the way out to 2 to the k minus 1 is equal to 2 to the k minus 1 like this. And just like last time, we're going to add our k plus 1 term so that our series side is now exactly what we want it to be, and we just have to do a little algebra on the right-hand side. So I'm going to erase here, and I'm going to now say, well, 1 plus 2 plus our series is now what we want it to be, k plus 1 minus 1. So it's just this whole series side with n is equal to k plus 1, which is what we want. And now it's time for algebra. We've got 2 to the k minus 1 from before, plus 2 to the k plus 1 minus 1 that we just added on. So I'm going to erase this to give myself some space. So we're going to do some algebra here, and we know we want it to be equal to this side, but with k plus 1 plugged in. So we know we want this to be 2 to the k plus 1 minus 1. So, time for some algebra. Here I'm going to simplify this exponent, and I've got 2k minus 1 plus 2k plus 1 minus 1 plus 1 minus 1 cancels out, and it's just 2 to the k. Now you'll notice you have two like terms here, 2 to the k plus 2 to the k. So I would rewrite that as 2 times 2 to the k, right? We've got two of those terms minus 1. Oh, rule of exponents, this is 2 to the first, and we have a common base here. And so we can write that as 2 to the k plus 1, since we add the exponents when we're multiplying their bases like this. Minus 1, oh look, that's what we wanted here. So we know we're done with our proof. I know that these are kind of weird. I just assigned a few. You'll notice here there's just 6 problems to give a shot. Here's the one presentation I'm looking for. Do your best. We're going to come back to it. They're proofs. They just take a little time. Sorry this video went a little bit long. Please leave any questions or comments in Google Classroom or drop by the Zoom. Talk to you later. Bye.